Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at the implementation of manifold learning methods that we looked at in the previous video. So before we do any coding, I just want to show you a couple of animations to get you more interested in this. So the very first one is the animation on the digits dataset by using the t-SNE method. So this is how it works. As you can see, all the digits images are separated. So this is 5. Let's find out where. Okay, 5, 7, 4, 6, and so on. Next, let's look at another animation. So this is the Swiss roll dataset. That's the generated dataset using t-SNE. Cool, isn't it? So next, let's look at the final one. So let's forward. Okay. For this is S-curve generated dataset, and we are using the MDS method. I hope you enjoyed these three animations. Now we'll look at coding, and I'll show you how to create the very first animation, and you can also use other datasets to put in place to get other animations working. So here, these are the libraries that I've imported. There are a lot of them. Some of them we need for visualization, others are for manifold, such as this one. We have for plotting, and then we have the data sets as well. And moving on, these are the versions that I'm using. Now, the very first uh, part that we'll look at is the digits data set. So work with that, digits. And for this, what we'll do is we'll create an animated scatter plot, just same as the one that I showed earlier. Animated scatter plot, and for this we'll first get the data x y is equal to data sets dot load underscore digits, return underscore x underscore y is equal to true, and then we can create the figure. So fig is equal to plt dot we probably don't need it right here. So we'll first create the for loop for I in range 250 to 500. These are the iterations that I'm setting. Minimum has to be 250, otherwise get an error. Here we can create the figure plt dot figure fig size is equal to, let's create a 10 by 10 image, and then we can create the model. So xe is equal to e for embedded, manifold dot t-SNE, and here we can specify a number of components is equal to 2, number of iterations is equal to I, because we are trying to plot these, and perplexity we'll set it to the 30. I think that's the default, and random underscore state is equal to 0. So with this we can fit and transform. So fit underscore transform x. So that is the model part. So we can add that here, model, and now we can plot this. So for plotting, plt.scatter xe, and here we use, there are two components so in the output, so we can plot those on the x and y axis. And then for color, we'll use the color based on the values in y. Then we can go ahead and annotate these. So for I comma txt in enumerate and y dot to list, and here to avoid adding the labels to each and every data point, I'm going to put a if condition here so that only some of the data points are labeled. Plt dot annotate str, so we convert it to string. Then you have xe I 0 and then xe I 1. With that, I think we are done with that main part. Now we'll look at the axis. So I'm going to switch off the axis. We can also specify the x and y limits. Then we need to specify display clear underscore output, weight is equal to true, and then display dot display cl.gcf, and then we can, I'm going to comment this out, but you can also put a sleep time here, such as say 1, so that each plot is delayed when it's plotted on top of other plot. Plt dot clear figure, and then this is for clear axis, and then plt dot close all. So let's see if this this works. Running this, and okay, so let's do one thing. We can set limits to the axis so we can see how the data points spread out. So here what I'm going to do is add plt dot x limit, and this can be minus 60 to 60. The reason why I'm putting it 60 is because I already know that within that limit we are able to see the entire animation played out. Okay, so we have that. Now if we run this, should be able to see. So this is the animation. So what you could do is you can use the same code. Just what you'll have to change is the datasets dot, and there you can change the dataset that you want to load. Or if you have some external datasets, you can bring that in and substitute the values for x and y, and that will get you this type of animation. So one point to note here is that in the digits, it's a toy data set, so we can see real nice groups of data points separating out. But if you look at some real world data sets, we'll look at one of those, which is mice protein data from openml repository, which borrows it from the UCL machine learning repository. So those data sets, we may not be able to see uh, such a good separation, but still it's a good exercise. So let's go ahead and stop this. You can play it out on your computer, and the video animation that I showed earlier, that was 20x speed higher. Uh, that was reduced to 17, I think 15 or 17 seconds. I'm going to stop this now. You get an idea of how this works. Next, we'll look at all the functions that we learned in the previous video. So to add models from each of those, what we'll do is we'll create a function that lists all these models in, and when we call the function on any data set, we get all the models run and the respective plots. So we don't have to type this over and over again. So this is the function that we have, plot this, which takes in values x and y. And here what we'll do is we'll create a list of models within tuples. The first one is LLE, and LLE, here we can specify the method or we can leave it as default. So here I'm going to specify the method standard. And next we have LTSA, and for this is LLE same. The only difference is we need to change the method to LTSA. Next we have Hessian LLE, Hessian LLE, LLE, and this would be again LLE. We change the method is equal to Hessian, and here what we can do is change the solver. Eigen solver is equal to dense, and next we have modified LLE, or modified LLE, and again here we can change the method is equal to modified. And next we have isomap, and for this we can, so for all of these we need to put manifold dot LLE manifold dot, because that's what we have imported. So I forgot to add that here. Next we have manifold dot isomap, and let's leave this as default. After this we have MDS, and for MDS again leave this as default, the MDS. Next we have spectral embeddings. So spectral embedding, so or just put a short form AC, and this is manifold dot spectral embedding. So this is capital S and capital E. And next we have the t-SNE. Again this would be capital t-SNE. And finally this is not a manifold method that we looked in previous video, but I'll add the PCA and n underscore components is equal to just to have comparison. Okay, and finally we need to plot all of this. So for plotting, let's uh, create a for loop here for I, and then label method in enumerate, and within this we specify the list, and then we can print this. So y is equal to method dot fit underscore transform x, and then we can specify plt dot scatter, and here we can specify y 0, and then we have y 1, and for colors I'll put c is equal to color, so that color is going to come from this y here. So let's change this to color, and finally we have cmap is equal to plt.cm.spectral, and that's optional part. Okay, so that's the figure that we have created, and finally we'll just add a title, a label, and plt.show. So all these plots would be sequentially plotted one below the other. And the first item that we can look at now is, we already looked at the digits dataset, so now let's look at another one. So this is the breast cancer dataset, and for this I will import the data. X, Y is equal to datasets. Datasets dot load underscore breast underscore cancer. Return X underscore Y is equal to true. And here we can specify color is equal to Y. Plot this X comma color and run this. So there's a scale manifold has no attribute LLE. So let's go back up and check this is good. Manifold LLE. So what I'm going to do is look at just the docs real quick and see what the LLE method is. So for manifold learning, this would be locally linear embedding. The reason why I put LLE there is because earlier I imported it as LLE. So here we haven't done that. We've just imported the manifold library. So now this should work. Okay, so that's the LLE. We have LTSA and we have another error. Neighbors must be greater. So what we need here is the number of neighbors that we can specify, and the number of neighbors right now I think the default is 5. So if we go back up here, let's copy this and put that here. Look at the docs. So here as you can see, the number of neighbors is n neighbors is 5. So for Hessian, what we can do is change that and increase the number of neighbors. So for doing that, I'm going to add this here, and instead of 5, let's make it 6 and then run this again. So this is the output we get. So we are able to see 2 separate groups. So let's look at these. So we have these blue and red that is separated of good for most part. That's the AC. And then this is the, I think this is for fit transform missing one required positional argument X. This is for t-SNE, and that's my mistake. What would the parenthesis there? Okay, so finally this should all be working. We have the Isomap. We can see 2 groups, but this is overlapping right here. For AC, we see these 2. For t-SNE, we can see these 2 separations, although there is some overlap or there. And that's the output of PCA, where we can see there's substantial overlap on this side. So that's how the breast cancer dataset worked. Now let's look at another dataset, which is the mice protein dataset from the openml repository. So let's type heading here, mice protein, and for this we need to import the dataset. And to do that, what we'll do is create a variable mice, and within it we import datasets dot fetch underscore open ml, and we can directly use this sklearn method to get the dataset by simply specifying the name of the dataset. And then here we can specify the version is equal to 4, and so that should work. And when we run this, uh, we should get the dataset. Now mice.data would have the dataset, which is the features, which are these. As you can see, this is the plasmid DNA, and then there are a bunch of other features there. and then if we type mice.target, these are the classifications. And so we are going to use these. Now what I've done is I've gone through a bunch of these and uh, saw that some of them give a better separation than others. So first what we'll do is we'll look at just the plasmid. So if we look at the columns, mice dot data dot columns, we have all these columns, and within these columns what I'm going to do is pick just the columns that have the P small letter P written in front of it. So I'm going to remove these, keep all of these, and remove these, and remove these, and again remove all of these, remove all of these, remove this one, keep that one, remove these. And the reason why is because with just these features there are less number of missing values, and so for the trial that we are working on, that that will make it easier. So is that, and then from this one we remove that and just keep these, and from this we remove all of this. So that's the final set of columns that we will be using. And in addition to this, later on what we'll do is we'll also filter out the targets, that is the y values. So we'll use that for now. And for targets, if we look at all the targets, so mice.targets, here mice.target. So we have several of these. And so can we do a unique on this? Okay, so we have 7 of these, 3 plus 3, 6, and 7, 8 of these. So what we'll do is instead of using all 8, we'll use just 2 of them to start with and see how it works, and then maybe add more to the data set as we go. So with that, let's get started with the next step. So what we'll do is we'll create a data frame. df is equal to mice dot data, and so this will now have all the columns. What we need though is just the columns that that have just the pDNA. So now we just have the before we do that, let's add the target column here as well. So df target and is equal to mice dot data, mice dot target. So now the data frame that we have has all these columns, and finally it also has the target column. So with that, now let's work on the filtering it. So x is equal to df, and the only columns we need here, let's first put y is equal to uh, before we do that, sorry, here what we need is df, and we need df target is equal to the target we need is, let's pick 2 targets. So dot is in, and within this we can specify the targets. Let's use this first one and use this, starts with letter S, and this one starts with the letter T. So with those two, we would now filter out several records, and with this again what we can do is get the y values. Now y is equal to df target, and then x will be equal to df dot drop, or rather than that we can specify pdna. So those will get us our x and y values. So y dot shape would be that, and x dot shape would be those values. Okay, so once we have this, I think we are in a position to now call the function that we created above. So that is plot this. So before we do that, we need to convert these values to numbers. So colors is equal to say 1 and 2. So for each of those two groups, and we need to factorize that. So y dot factorize, and then plus 1. So this will be pd dot factorize y 0 plus 1, and we'll look at the colors. So that is good. Now we can call plot this, specify x and colors, and run this. Plot this, and here we have an error, contains NaNs. So the reason why we are getting this error is because the data set has, so if you look at x, there are values that are either some values are missing, so we can check that. So if you look at x dot is na dot sum, so we see that this PCFOS that has 45 missing values. So what I'm going to do for now, just remove that column and then rerun this. So rerun this, and then we get the data. Now we have all values are good, and we get that, and then run this one. So now look at what the plots look like. So LTSA, Hessian, Isomap, MDS, SE, t-SNE. So this is for t-SNE. As you can see, there's not a good separation that we expected. We do see a lot of overlap, and that's the PCA. So this is a kind of trial and error. You can play with this and see if you can get a better separation by trying different strategies. So one point that we didn't do here is normalizing the data set. So what I would do is where we have where the x values come in the function, we can add normalizing step. So this is where we have the x values that come in, and we have the x there. So let's go ahead and normalize this. So x is equal to preprocessing dot standard scalar and dot fit underscore transform x. So with that, we'll try to run this again. Let's run the breast cancer data set as well and see if it makes a difference. And okay, so we do see difference here. So we can, in the t-SNE, we see a very nice separation. As we can see it for the PCA and for the simple SE as well. Now we'll run the same function again for the mice dataset. So here we are. Now when we run this, we get an error. Invalid argument RGBA to RGBA1. The error is because there is mismatch in the number of rows. And that is because we didn't run the mice dataset again. So I'm going to run this all over again. And then we have these, and now when we run this, Let's see if we get a better separation than the previous attempt. So we do see separate groups, but still there is a lot of mix going on. And now if we were to change the targets that we selected, so here we have selected these two. Let's see, instead of CS, if we use the SC, and instead of M, let's use S and run this again. So let's go back up and run everything again. Okay, so this has infinity values, uh, but this should not have been there because okay, possible. So what we can do is, because there are NNs in there, we're going to fill them. So x dot fill NA, and we'll fill them with zeros. So we'll run this, and there were 3 NNs in there, and now when we run this one, okay, MDS, and now it's starting to look better for this particular set of targets. So as you can see, there is a clear separation of the red and separation of the blue, but ideally what you would expect is that these would be clustered together and this would be clustered together into one simple group, and that's not what is happening here. So what there are a couple of possibilities that you could try, and I'm going to show you one of those. So what we can do is just copy this, and if you can write a separate code where we don't have to run all these methods all over again. So xe is equal to manifold t-SNE, and then we can plot these. So for plotting, we can simply again copy paste same code that we have up above, which is this one. Copy and paste it here. So what we'll try to do is we'll try to change the perplexity and other parameters to see if that makes any difference. So we don't need that. And here I'll just use XE for embedding. XE, and the color, it's all going to stay the same. Manifold dot t-SNE question mark, and here we get this guide. So first item will change is perplexity is equal to, so this is 30 right now. We can plot it for 30. t-SNE is not or sorry, we need the fit underscore transform x, and let's see what there are. Invalid RGBA, probably mismatch between the values. So here we have the x dot shape, which is 285, and then colors dot, sorry, colors dot shape, and that is 285. So here this needs to be an S. Label is not defined. Yeah, we don't need the label here. Okay, so that's what we get when we have the perplexity of 30. We can add random underscore state is equal to 0, and then add n underscore iter is equal to 1000, and then in addition to this we can also add learning underscore rate. So you could tune all of these parameters, hyperparameters, to see which one gives the best results. So with these default values, this is the type of plot we are getting. We can I'll try to change couple of these And just to show you the drastic effect it can have. So first is perplexity. If we change it to 0, you see we get a value which is the output is completely random. And if we change it to a higher value, say 100, again the data set it's different than what we had earlier. Still we do not have a compact group. Let's put that back to 30. And learning rate, again, if we have a low learning rate, let's say put as 1, we get different value. If we set it to 50, we get another set of values. So I tried several combinations, but for this particular case, for the protein database, the best I was able to get is this. You could try different combinations of the plasmid DNA or the columns and the different combinations of target and see what output you get. So that was it for this video then. I hope in this video you learned how to implement manifold methods in Scikit-learn uh, on both the toy and real world data sets, and also how to create cool animations that you can add to your presentations. In the next video, we'll continue studying about unsupervised learning methods in Scikit-learn. Until then, please like, share, and subscribe. Thank you.